Hey folks, in one of the previous discussions we touched upon vector dot product, and I want to emphasize that a lot more now because it's something that we're going to be using a lot in this class, okay? From here on in, we're using vector dot product a lot. So I'm going to try to run you through just a brief lesson on what vector dot product is and kind of walk you through it. And hopefully by the end, it'll be like, oh, that's real easy. And that's what I'm hoping for anyway. By the way, for a few of you really mathy types, there's also going to be something called a vector cross product, which is somewhat significantly different than dot product. And we'll talk about that when we come to that. All right, so for dot product, a reminder, it's just a measure of how parallel two vectors are, okay? And it can be plus, minus, or zero. Now, another thing that's important about dot product, a dot product is a scalar. Now, you use two vectors to find a scalar. So on the previous video, we did work as force dot delta r. Force is a vector, it's got a direction and measured in newtons. And delta r is a vector, it's got a direction measured in meters. When you dot product those, you get a scalar, you get work. You don't say work to the right or work up or work at 30 degrees north of east or anything like that. Work is a scalar. It's like money. Money's a scalar. You don't have a direction to it. Now, by the way, another note on that, force times displacement is newtons times meters. That's equivalent to a joule. A joule is defined as a newton times a meter. Okay. All right. So in our little sketch here, if you need a moment to pause the video and copy that, go ahead and take it. All right. So what I've got here is a book or something, and I'm pulling it to the right. And delta R is to the right, and that's 5 meters. Okay. And I got 4 different forces, A, B, C, and D. Okay. And they're acting in different directions. And by the way, the B and D are probably the normal force and the weight of the book. That's fine, you know. Maybe the A is you're pulling the book, and maybe C is friction or something like that. All right, so if I were to ask you, what's the work done by the 4 Newton force? Okay, so the work done by A. All right, well, first of all, plus or minus or zero. Hopefully you understand it's plus. The A is in the direction of the delta R, okay? And you would just do force delta R, so it'd be 4 times 5, and you would get plus 20. And it would be joules if these were newtons and we were moving in meters. The work done by B would be a big 0, right? Because B is perpendicular to delta R, so it doesn't do any work. There's no part of B that's in the direction of delta R. The work done by C, plus, minus, or 0, well, that's the opposite direction of displacement, so it's minus, and that would be 2 times 5, which would be minus 10 joules. And finally, the work done by D, just like the work done by B, would be 0. Okay. Now, believe it or not, you're on your way to understanding dot product. Okay. Now, in my second example, we're going to make this look a little more complicated, but not really. Let's say I give you a vector that looks like this. Okay. And I'll call that vector, I don't know, E. Okay. And vector E is 4i hat plus 3j hat. Now, you may notice something. If you look at the previous example, that's a combination of vectors A and B, right? Okay, so that's vector E on this page. And again, let's say we move to the right 5 meters. What's the dot product? What's the work done by force E? Okay, well, how you would write that is you would write E dot delta R. And you would write E out in unit vector notation. So 4i plus 3j dot, and by the way, it's dot, not times, but dot, and then you would say 5i, okay? So how do you do this? Well, if you look back at the picture here, what did we do up above here? Well, A, you multiplied 4 times 5. For B didn't do any work. Well, you're basically doing the same thing here. You've got 2 components of this vector, one pointing to the right and one pointing up. Only the component pointing right is going to do any work. That's your 4i. So what you're doing is you're taking 4 times 5, and you're going to get positive 20. And if this were newtons and meters, this would be joules. In other words, you ignore the 3 in this case. It's not that part of the vector is not parallel to your displacement in any way. So your answer would be positive 20 joules. Same as when you added these two together up here, okay? So what you learn? Well, when you're doing dot product in unit vector notation, you multiply the like terms. You i's times the i's, and eventually j's times the j's. And if you're doing a 3D vector, it would be k times k as well. Okay. All right. Next part of the example here. Let's say I give you the following. Okay. I give you a vector f, let's say, and it is a magnitude of 5 newtons. And the angle with the horizontal is 36.9 degrees. And again, you pull this thing 5 meters to the right. How much work does F do? All right. Well, even if you had this problem last year, hopefully you kind of remember how to do it. It's pretty simple. You would find the component of F that is perpendicular or parallel to your delta R. How would you find that parallel component? Well, you would do 5 times cosine of the angle. That's the component of the force that's parallel to the displacement. And you take it times the displacement, which is also 5 in this case. Now, you can rewrite this. You can say 5 times cosine of the angle. Okay. Now, so in other words, you're doing F, the magnitude of F, times the magnitude of, and I'll write that correctly, delta R, times cosine of the angle between them. Okay. And if you do that, you can try this out in your calculator, but you're going to get positive 20 within rounding. You're going to get positive 20 joules because guess what? This is a 3, 4, 5 triangle that I've drawn for you. It turns out that angle in there is 36.9 degrees. Same thing up here. That angle will be 36.9 degrees. Okay. That's not an accident. All right. Now, where does this all lead us to? Okay. Well, there's a general equation for dot product. Dot product is, if you take vector, the first vector, let's call it A, and you dot product with the second vector, let's call that B, that equals the magnitude of A times the magnitude of B times cosine of the angle between them. Okay. This is a definition of vector dot product. This half of the equation, you're going to use unit vectors. Okay. So that was like what we did right here, okay, that we use unit vectors. The second half of the equation is what we just did, right there. We took the magnitude of A times the magnitude of B times cosine of the angle between them, okay? All right, so let's try a couple examples, just general examples with this. Let's say I gave you 2 random vectors, okay? Let's say one of them points due left, and we'll call that A, and let's say that's equal to 6 units. And let's say B goes this way, and that's equal to 5 units. And let's say this angle here is your 36.9 degrees right there. Okay, so vector B is a 3, 4, 5 triangle, okay, because that angle is 36.9 degrees. Now, having said that, we're going to figure out A dot B, okay? Now, you got to be careful. When we say the angle between them, well, actually, back up a second. Would you expect this vector dot product to be positive, negative, or 0? Okay. Well, A and B are pointing somewhat opposite directions to each other. So you should expect a negative vector product here, vector dot product. However, if I do vector A, so if I do 6 times 5 times cosine of 36.9 degrees, I'm going to get a positive answer out of that. That's because 36.9 is not the angle between the 2 vectors. This is the angle between the 2 vectors. You start on the first vector and you sweep to the second. That's the supplement of 36.9, which would be 180 minus that, which would be 143.1 degrees. Okay, so that's what you're going to do. Now, we're going to do this 2 ways. Let's start with the left-hand component of this. So the left-hand side, I'm going to do the dot product. I'm going to use the unit vectors. So if I write A in a unit vector, it's negative 6i plus 0j. And if I write B as a unit vector, if I do the cosine, 5 cosine 36.9, I'm going to get 5i, okay? And if I do 5 sine of 36.9, I'm going to get 4j within rounding, okay? So if I do A dot B, this is a unit vector stuff, it's going to look like this. You're going to have a negative 6i plus 0j dot 5i plus 4j. And here's what you do. You do like terms. So you multiply the i's together and you multiply the j's together. So you're going to have negative 30. Okay. Oh, I'm sorry. I wrote this down wrong. B is 4, or I'm sorry. B, oh my gosh. B is not 5 and 4. Oh my gosh. Can you guys change that for me? It's 4 and 3. Oh my gosh. So this here's a 4 and that here's a 3. Oh, that would have been catastrophe there, wouldn't it? All right, 4 and 3. All right, so we do negative 6 times 4, and you get negative 24, and then plus 0 times 3 is 0, and your answer is negative 24. So that's the dot product. Now, there's no vector on that. It's a scalar. It's not a vector. It's just a measure of how parallel, or in this case, anti-parallel, the two vectors are. Okay. Now, that was the left side of the equation here. The right side of the equation should be the same, right? If I do the magnitude of A times the magnitude of B times cosine of the angle between them. So the magnitude of A is 6, the magnitude of B is 5, and you would do cosine of 143.1. If you do that in your calculator within rounding, hello, you're going to get negative 24. So duh, it's an equation, there's an equal there, they better be equal. But if you don't believe me, try it out. By the way, make sure your calculator's in degree mode, not radian mode if you do this, okay? All right, now I've got another example for you. Let's try that out. Let's say A, and I'm gonna draw this a scale just so you can see it, is negative 4 comma 2. So 1, 2, 3, 4, 1, 2. So A goes like that, and it is negative 4 I hat plus 2 j hat. And then B is going to be 5 comma 7. So from here we go 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. I'm way up there. So there's B. Okay, and that is 5 comma 7. Okay, or 5 I hat. Sorry. Well, I'll write it this way: 5 I hat plus 7 j hat. Let's write it that way. Okay. All right. So here's what I want to know: what's the angle between them? Okay. Now, if you just look at this angle, what does it look like to you? If you had to guess right now, what would you guess? Okay. Hopefully, you're looking at that and saying, hey, it's maybe just a little bit bigger than 90. Okay. So by the way, should our dot product be plus, minus, or 0? Well, any angle bigger than 90 should give us a negative dot product. So we should get it when we're finding the angle, we should get a negative dot product. Okay. All right. Well, here's what we're going to do. Okay. We're going to do A dot B. That's the unit vector stuff. That's equal to the magnitude of A times the magnitude of B times cosine of the angle between them. Okay. All right. So we've got for A, it's negative 4 I hat plus 2 j hat dot B, which is 5 I hat plus 7 j hat. That's equal to the magnitude of A. So you would do this Pythagorean theorem. You would do 4 squared plus 2 squared. That's 20 square root. So I'll just write square root of 20 times the magnitude of B. That would be this 5 squared plus 7 squared, which would be 74 square roots. So times square root of 74 cosine of this angle that we're trying to find. Okay. Now, when you do dot product, you multiply the i's together and then the j's together. So negative 4 times 5 is negative 20, plus 2 times 7 is 14. That equals all this stuff. And so we get negative 6 equals root 20 times root 74 cosine of that angle. So first of all, our dot product is negative, as we suspected. And I did this out in my calculator. If you take negative 6 divided by root 20 divided by root 74, I get cosine of the angle. I got negative 0.156 roughly. And then the angle, I got about 99.0 degrees. So just over 90 degrees, okay? So that's a way in math they would have you use dot product to just straight up find an angle or something like that, okay? Now, as far as work goes, okay, one last example. Let's say I gave you something moving around, and its starting position was 2i plus 7j, and its final position was negative 4i, don't call me a 4i now, plus 10j, okay? Let's say while it moved from point 1 to point 2, a force acted on it, and that force was a two-dimensional force, and it was negative 2i plus 3j, okay? let's find the work done. Okay. Now, to find the work done, the work is force dot delta R. Now, there's two ways for me to do that. I can either use the unit vectors, or I could do the magnitude of the force times the magnitude of delta R times cosine of the angle between them. Since I don't know the angle between them, and I really don't care to find it, I'm going to use the unit vector part of this, okay? Now, before I do that, though, I need to know what delta R is. What is delta R? So I'm going to take delta R, which is R2 minus R1, okay? So we got R2 minus R1, so negative 4 minus 2 is negative 6i, and then in the j direction it's 10 minus 7, which is plus 3j. So that's our delta R. All right, so our work is force, which is negative 2i plus 3j, dot our delta R, which is negative 6i plus 3j, okay? And then here we're going to multiply like terms. So here's the i's and there's the j's, right? So we got negative 2 times negative 6, which is 12, plus 3 times 3 is 9. And our answer would be positive 21 joules. Now, again, there's no vector there. It's a scalar, okay? We're using vectors to determine a scalar quantity. All right, I do have one more note to make for those of you at LT doing a problem set shortly. There's one quick hint I'm going to give you on one of them. Before I do that, though, hopefully this was helpful in learning what dot product means. And a reminder, it's very basically speaking, it's simply how parallel are two vectors. But now we have a mathematical way to model that or to calculate that. Now, one last thing. If for those of you at LT, you're going to be doing a problem that has 3 dimensions, I, J, and K. It's the exact same process, okay? But then they might ask you to find the magnitude of a 3-dimensional vector. So let's say I gave you R was, I don't know, 2i plus 4j minus 7k. And I said, how long is that, okay? Well, all you would do is I like to call it super Pythag. You would do 2 squared plus 4 squared plus 7 squared square root, and you get an answer. Okay, so if you're trying to find the magnitude of a 3D vector, that's all you do. There's all kinds of proofs of that online. If you look at a rectangular solid and make it I, J, and K, you can kind of quickly prove that. So I hope that was helpful, and thank you very much.